So today I am going to be talking to you all about some very exciting work that the Duvet survey team has been doing, mapping outflows in starbursting disk galaxies. And so an outflow occurs when gas moves outwards from a source. For example, in this artist impression, we have a supernova exploding within a galaxy disk, and it's pushing gas outwards. Some of that gas will leave the plane of the galaxy, maybe to enrich the surrounding CGM or to fall back onto the galaxy in a galactic fountain and be recycled to the next generation of stars. And some of that gas will expand within the plane of the galaxy itself, introducing turbulence into the surrounding gas cloud and affecting star formation processes within the galaxy. So by observing the outflows which break out of the galaxy disk, we can better start to understand the feedback effects which are occurring within the disk of the galaxy. And as well as being an observational tracer of star formation feedback, outflows are an integral part of the baryon cycle. So one of the most well-known galaxy-wide outflows is in M82. M82 and its galactic outflow have been studied in extreme detail over many decades, and it's the basis for many of our models of galaxy winds. However, we still don't have a single model that well represents this outflow in all of its phases. In addition to that, M82 is only one galaxy, so we should expect some change in how outflows work with time, with galaxy mass, and possibly even with galaxy metallicity. We could just be catching M82 in a specific phase of its outflow cycle, and so to get a better handle on these sorts of questions, we need to be building samples of galaxies with a large range of properties, where we can do spatially resolved studies of outflows in different environments. And this is where Duvet comes in. Duvet is a survey of starbursting galaxies in our nearby universe. So here we have a plot of star formation rate against stellar mass. In grey are SDSS sample galaxies with the dashed line showing the main sequence. The blue points are Duvet galaxies. So Duvet galaxies are chosen to be starbursting and compact. They have star formation rates 5 to 15 times the main sequence value. This means that they have really high star formation rate surface densities. They're also chosen to be disk galaxies with well-ordered rotation fields and exponentially decreasing profiles, so we don't have any crazy kinematics going on. There are currently 27 galaxies in the Duvet sample, which have been observed using KCWI. Because Duvet galaxies are compact and in our local universe, they fit nicely into the field of view of KCWI. This means that we have spatially resolved data for all of our galaxies on scales of a few hundred parsecs. We also have data from ALMA and GMOS, and some of our targets overlap with HST-COS observations, so it will be possible to compare outflow measurements in different phases of gas. We have a range of both edge-on and face-on galaxies in the sample, as shown in these pictures. And this enables us to study outflows from both the side and also looking down the barrel. So we can start to map out a large range of outflow properties. So I'm going to be giving you all a very quick tour through some of the things we've been working on within the Duvet team. And I'll keep on coming back to this little cartoon galaxy, just so you know which way the disk is and which way the outflow is. One of the large uncertainties in outflow studies is the extent of the outflow. So if we focus on this side of our cartoon edge-on galaxy, we expect the flux to decrease as we move off the plane of the galaxy, and the velocity dispersion to increase as the outflow spreads out, and there's a greater range of velocities observed as we look through the side of the outflow cone. We can observe this happening in Markarian 1486. So this is a flux map of the galaxy. We can see the edge-on disk along here. And in contours over the top, the increasing velocity dispersion where the outflow cone is. And this is something which Daniel McPherson has been working on. So here, Daniel has plotted the 03507 flux and velocity dispersion as we move off the minor axis of Markarian 1486. Daniel has been using these two quantities to create a new method to define the extent of outflows in edge-on galaxies. This is a work in progress, but keep an eye out for more results which are coming soon. So once we know where the outflow is, we want to know a bit more about its properties. So just for fun this last week and a bit, I've been playing around with our O2 doublet data for the edge-on galaxy KISSA 1578. to find electron densities for the outflowing gas. This is only possible because we have such high signal to noise data. So this is a quick map which I've made of the electron densities with median flux contours overplotted to show roughly where the galaxy disk is. And so if we concentrate on this part in the middle, where the outflow is, and take the median values, then I can make a profile of the electron densities going off the disk into the outflow. So it's very often assumed that outflows have a high electron density of around 300 per centimeter cubed. But what I'm finding in KISSA 1578 is actually really very low electron densities. Of course, this is very preliminary work and it needs to be extended to more galaxies in the Duvet survey. So before I start talking about metallicities, I just want to acknowledge that some of you are extreme experts in this area. For the rest of us, here is your one slide refresher. Metallicities are commonly measured in galaxies using the strongline method. This assumes a model with a particular relationship between the ionization, the electron density, the pressure, and the metallicity. And this works quite well when we look at galaxy disks and we understand how all of these things interact and work. But as we move off the disk into the outflow, as I just showed, the electron density changes. And we don't always understand how this actually happens in an outflow. And so we'd prefer to measure metallicity with something like auroral line metallicities, which depend directly on the electron temperature. However, auroral lines tend to be 50 to 100 times fainter than strong lines. Luckily, we have the 034363 line with a signal to noise of 5 out well past the disk on both the minor and major axes in Markarian 1486. And so Alex Cameron has been working on this. He used the 034363 line to map metallicity in Markarian 1486. And so the areas of highest metallicity are off the minor axes, above and below the plane of the disk. The areas of lowest metallicity are at the edges of the disk on the major axis. So this suggests that Markarian 1486 is being fed by a very metal-poor inflow. The gas is then converted to stars, and the star formation is driving an outflow of metal-enriched gas. And as V said, this work has been published in a recently released paper. Check the archive and look out for the media release, which had that super cool video which we saw earlier. So edge-on galaxies are great for getting the shape of the outflow and for mapping outflow properties away from the galaxy disk, but they lose the vertical velocity information. So we need to also look at face-on galaxies as well to get a holistic view of outflows. By looking at face-on galaxies, we're looking straight down the outflow cone, and we can now start to compare that vertical velocity information with resolved properties of the galaxy. And this is something which I have been working on. So I've found evidence for outflows across the face of IRSO 8 and have been able to measure their outflowing velocities, which is what I have mapped here. This suggests that starbursting galaxies don't fit the same biconical outflow structure which we expected from our studies of M82. It's possible that starbursting galaxies have a far more complex baryon cycle. So as gas is outflowing from the galaxy disk, driven by star formation, it may be impacting into gas which is returning to the disk from previous outflow episodes, creating a lot of turbulence in the environment around the galaxy. But we don't just want to look at where the outflow is, we also want to understand the driving mechanisms behind that outflow. So here we have two subgrid physical models. Both are used in simulations to represent outflow behavior in galaxies. So energy-driven winds are primarily driven by supernovae exploding and giving energy to the surrounding gas. Momentum-driven winds are primarily driven by radiation from young massive stars. These two models have different relationships between the star formation rate surface density and the outflow velocity. Momentum-driven winds are sometimes used in simulations to make galaxies quench faster, since in those models, a higher star formation rate launches outflows with a much, much higher velocity. And this allows them to push gas out faster and at velocities where it can escape the galaxy. The different relationships between the outflow velocity and the star formation rate surface density also mean that we can tell these two models apart observationally. And so this is what I've done. Here is the maximum outflow velocity I have measured against star formation rate surface density for spaxels in IRSO 8, where I have found evidence of outflows. And as we can see—
2 minutes, Bron.
Thanks. The outflows in IRSO 8 are consistent with energy-driven outflow models. And so in summary, the Duvet survey is starting to fill in the picture of outflows in starbursting galaxies. From our edge-on galaxies, we're using the flux decrease and the velocity dispersion increase off the minor axis to define the extent of outflows. We've found evidence that the galaxies are fed by metal-poor gas inflows, and that the outflows are metal-enriched and may have very low electron densities. From our face-on galaxies, we've found that starbursting galaxies may have a very complex baryon cycle, and that the outflow in IRSO 8 is consistent with energy-driven outflow models. Thanks.
Thanks very much, Bron. That was great. All right, I'll just check the Slack. Okay, so nothing yet, but while we wait, time for a quick question. So I was wondering, I think this was a preliminary result, one of your first ones, but where you found like the lower electron densities than you'd expect in the outflows at the start.
Yeah.
Do you know, would there be a physical reason for that you'd expect that, or not thought about it yet?
I haven't particularly thought about this yet.
Yep,
I was just very excited to get it.
Yeah. Yeah, no worries. That's cool.
Yeah.
All the questions are coming in the Slack now. Okay, so one quick one. How does the observation of outflows across the entire disk in IRA SO8 relate to the observation of enhanced metallicities in a biconical structure in the edge-on galaxy? Are these galaxies thought to have different outflow structures?
I have yet to measure the metallicity of the outflow in IRSO 8, but I think that's on our list of things to do. And I wouldn't expect them to have hugely different outflow structures since they're both starbursting galaxies, but there may be some differences.
Awesome, thank you. And there's a few more questions coming in now, so I'll just encourage you to check those.